Hello everyone, and welcome to a new episode of the Virtual Lab series of video blog presentations on various diverse scientific computing topics. As you can see here, the topic of today's presentation is on how first principles simulations can contribute to understanding the chemical reaction mechanisms underlying the removal of contaminant heavy metal ions from polluted water. So, let us begin our main scientific presentation of today. Water is a vital necessity for human life. However, contaminants in our drinking water can easily enter our bodies, leading to fatal illnesses or even death. The lack of safe drinking water is a pressing global issue, particularly in countries grappling with water contamination and scarcity. According to the United Nations Environment Programme, UNEP, in 2016, over 300 million people consume polluted water, and 3.4 million people succumb to waterborne diseases annually. Common water pollutants include nutrients, organic matter, oil, metals, and pesticides, some of which are naturally occurring. Yet, the main source of pollution is human activity, including industrial waste, domestic sewage, and agricultural or livestock wastewater. The pollution levels from these human activities continue to increase at a steady pace. Among the various sources of water pollution, heavy metals like arsenic, chromium, and lead are frequently found in industrial wastewater and natural environments such as mines, groundwater, and rivers. Even small quantities of these metals in drinking water can cause severe and lasting harm to humans. Therefore, it's crucial to manage our water sources diligently. Once heavy metals enter the human body, they are not metabolized, and prolonged exposure, even at low levels, can lead to various diseases. These toxic metals often exist as complex ions, up to 1 nanometer in size, in natural water bodies. Therefore, standard filtration methods aren't effective for their removal. Instead, techniques involving chemical reactions with heavy metal ions, like ion exchange, adsorption, precipitation, and biological treatment are used. Of these, adsorption is the most commonly employed because it does not generate byproducts and requires relatively simple post-treatment. For this method to be effective, the adsorbent must be economically efficient, environmentally friendly, and capable of absorbing and removing heavy metal ions. It's also worth noting that adsorbed heavy metal ions can be released back into the environment under changing conditions, such as temperature, acidity, pH, and interactions with other ions. This could potentially lead to environmental contamination. Therefore, it's important to understand and control these desorption conditions. To create effective adsorbents, we must consider the interactions between heavy metal ions and the adsorbent, as well as the impacts of the surrounding environment. In terms of gas adsorption, the mechanism is fairly well understood, as both the surface of the adsorbent and the toxic gases in the air typically maintain stable forms. However, in water, molecules interact strongly with each other, creating diverse molecules or ions. The surface structure of the adsorbent also changes underwater, impacting the adsorption mechanism and the adsorbent's zeta potential. For example, chromium forms different complex ions depending on pH levels and adheres to carbon materials through several steps. Given the many factors influencing liquid phase adsorption, it remains challenging to fully understand the mechanism, despite ongoing advances in experimental and analytical techniques. Over recent decades, computational science has seen significant advancements, thanks to a well-founded theory of computation and the progression of computational power. Among the various methodologies, density functional theory, DFT, has proven to be particularly useful. DFT is designed to calculate the electronic structure of materials and, in doing so, helps understand their properties, such as optical characteristics, vibrations, structure, and conductivity, and interactions, all based on quantum mechanics. As such, it provides highly accurate simulation results, especially in examining a wide range of nanoscale natural phenomena. Its applications have consistently expanded since the 1980s when research in this area took off. Recently, DFT techniques have shown impressive results in simulating energy storage and catalytic reactions, building on their prior achievements in physics, such as predicting physical properties or identifying causative factors. Despite these successful applications, DFT has its limitations. For instance, it can only calculate up to a few thousand atoms due to the swiftly increasing computational costs in proportion to the size of advanced computing systems. As previously mentioned, the mechanism of liquid phase adsorption involves a variety of reactions, making it difficult to comprehend the impact of each individual reaction on the final adsorption step. Particularly with reactive and unstable entities like toxic heavy metal ions, the complexity of the adsorption mechanism increases further. Thus, applying density functional theory, DFT, for independent analysis of each reaction within the overall adsorption mechanism could be beneficial. However, it's important to note that DFT is capable of handling only limited spaces. Therefore, calculations must be performed while considering results from experimental analyses or specific situational models. On the flip side, interpreting experimental analysis or measurements can involve uncertainties. This necessitates conducting DFT-based measurements and analyses to yield reliable results. Consequently, collaborative research between experimental measurement analysis and computational science is essential. These fields can complement each other to shed light on complex liquid phase chemical reactions, such as the adsorptive removal of heavy metal ions. This brings us to the conclusion of our presentation. Many thanks for your attention. This presentation was provided in partnership with Virtual Lab, the company behind the development of the Materials Square online platform, for executing atomistic materials and chemical computations directly on the cloud. We therefore recommend to please give a try to the Materials Square simulation platform by visiting its corresponding website at www.materialsquare.com, or more shortly matsq.com, as noted in the present slide, or alternatively also in the video description below. Furthermore, please do not hesitate to contact us by email, as also shown here on this slide, in case you would like to obtain further information on the various R&D services and solutions for materials and molecular modeling applications that we can provide at Virtual Lab. Many thanks again for your interest and your consideration.